All right, so that was the growth we looked at before. Now we're going to look at half-life. And most half-lives deal with radioactive isotopes, and so that's what we're going to look at here. And the rate of decay for a half-life, if our T is known, and most radioactive isotopes, we know the T, so we can calculate our K, is going to be negative ln of 2 over T. Okay, so that's how we calculate K. So this one says the half-life of plutonium-244 is 80 million years. So that's a long time for a half-life. Okay, so if we start with, 100 grams, in 80 million years, we'll be down to only 50 grams. Okay, so that's why, we have long periods of time for these half-lives. Now, find the function that gives the amount of plutonium-244 remaining as a function of time measured in years. Okay, well, that means we have to get us a function that's going to be, I don't know, maybe life at time t is going to be some a naught e to the kt. So we're looking for this kind of a function. So first we have to find this k. Well, k is going to be minus ln of 2 over t, which is 80 million years. All right. And we can figure that out in our calculator. So let's type that in. Now we can say, okay, well, we want the a negative. Okay, well, we have to get out of here. Negative ln of 2 divided by 80. 1, 2, 3, 4, 5, 6. So we get negative 8.66 times 10 to the negative 9. So that's a negative 8.66 times 10 to the minus 9. So that's our K. And we know our A naught here. Nope, we don't know our A naught. So depending on how much we have, this is going to be our equation. So it's just going to be L of T equals A naught E to the negative 8.66 times 10 to the negative 9 T. Okay. And so that will be our amount of stuff remaining after so many years. So if we had, a T of 5 and a naught of, zero point 0.1, that's not going to be very much. It's still going to be about 5. But if you start looking on the time frame in millions of years, that's when you're going to start noticing a difference. So that would be our function that we have to use to find how much is left after, 10 million years or something like that. All right, radiocarbon dating. This is using carbon 14. Okay, now this is a special thing that scientists use to date, things that have carbon in them, like wood or bone or things like that. And so we can use carbon 14 dating to do that. And so what we're going to do is we're going to express the given percent of carbon 14 as an equivalent decimal. So maybe we had 20% carbon 14 left. Well, that's going to be equal to basically uh, uh, 0.2 because we have to convert that to a decimal. So that's the key. We have to convert whatever percentage it is to a decimal, and then we're going to substitute k into the equation t. And so this is a specific K for carbon 14. Then we can plug in our R value and we can solve for T. Okay, so that is how we're going to use it. But now there's only a few questions in our book on how to do this, but this is something where they give us our K and then we plug in ln of R and we can do it. What I want to do is I want to do an actual example where we have to go and do the calculation and figure out something and plug in and solve for our K, and then we can, after that, solve for our T. So here we have cesium-137 has a half-life of about 30 years. If we begin with 200 milligrams of cesium-137, will it take more or less than 230 years until 1 milligram remains? All right, well, again, let's start with our original equation, y equals a naught e to the kt. Now, what do we know? Well, we know that it has a half-life of 30 years. And if we start with 200 milligrams, how much is half of that? Well, that's 100. So let's say we have 100 equals 200 e to the k times our half-life of 30 years. So we've plugged in everything we know, the half of 200 and our half-life of t is equal to 30, now we can solve for k. Well, if we divide by 200 and divide by 200, we have 1/2 equals e to the, well, we can say 30k maybe. How do we get rid of that exponent? Well, we take the ln of both sides. So the ln of 1/2 is equal to 30k ln of e, because we can bring that down to the front now. Well, that's just 1. Divide that by 30. So k is equal to ln of 0.5 over 30. Now, we could actually calculate that and stuff like that, but it's going to be a nice, well, I shouldn't say a nice, it's going to be a long decimal. It's not going to be a simple one. It's going to be, negative 0.0231496, and that's as far as our calculator takes it. So to get an exact number, we're going to leave it like that, okay? Now, what we want to do is we want to find out how long it takes until only 1 milligram remains. So how do we do that? Well, we know our K now. We know our initial value. We know what we want to plug in. And then from there, we can solve for T, because we have the K, we have the A naught, and we have our Y. So we plug it all in. 1 equals 200, and then we have e to the ln of 0.5 over 30 times t, okay? Now this isn't any different solving than we did here, except here we solve for k, here we're solving for t. Okay, so what do we do? Well, we're going to divide both sides by 200. So 1 over 200 equals, now we'll put e to the ln 0.5 over 30 times t. And so then we're going to take the ln of both sides. And so again, this comes down in front, and then our ln e disappears. So we have ln of 1 over 200 equals ln of 0.5 over, oh, not the whole thing over 30, and then times t. We want t, so we're going to divide by the ln of 0.5 over 30. Divide that by the ln of 0.5 over 30. And so this should give us what t is equal to. Okay, so what do we have here? Let's see if we can type that in our calculator and get an answer. Well, we're going to take the ln of 1 divided by 200, and that's going to be divided by the ln, and that's going to be of uh, 0.5 divided by 30. What did I divide here wrong? Oh, it is, I'm doing it wrong here. Let's do this. That is, all right, so we put our extra parenthesis here. That is the ln of 0.5 divided by 30. All right. So 229.3 years. So let's fix that, because I did have it over 30. I just saw that on my thing. So this is over 30, that whole thing. So this is whole thing is over 30, not just that. So it's ln of that. So I have to make sure I keep track of what I have everywhere. Otherwise, you're going to have the wrong answer. And so T, it said, was 229.3 years. And so that's how long it was going to take to decay to that 1 milligram. Now, it says, will it take more or less than 230 years? It takes less than 230 years. Now, not much less, only 0.7 years less, but it does take 0.7 years less to do that. So that was the whole key on this one. It's just a very little bit less, and so that's the key there. All right, double time. How do we calculate that? Well, it's going to be t is equal to ln of 2 over k. And whenever you're doing these, remember, we can say, well, k is equal to the ln of 2 over t. We can swap those around. So if we know one or the other, we can swap to get the other one very easily, because, if we took here times k and then times k and then divided by the t, so divide by t and then divide by t, that's how we get to doing this. And so, that ends up with k as ln of 2 over t. And so basically all you do is just swap your t and your k. So it says recent data suggests that as of 2013, the rate of growth predicted by Moore's law no longer holds. Growth has slowed to a doubling time of approximately 3 years instead of every 2 years. And that's just because that's what Moore's law said. Find the new function that takes longer doubling time into account. Okay, well, how are we going to do that? Well, we need to figure out what we have as far as numbers. Well, we know that here, this looks like t is equal to 3. So what we can do is we can plug that 3 in here and find a new k constant, which is going to be ln of 2 over 3. Now, we could go ahead and solve that, but if we want to be exact, we'll leave it that way. And so our doubling time, and to count, so growth then, maybe let's call it growth at time t is equal to, well, we don't know what a naught is, so we'll leave it as a naught. And then it's going to be e to the ln of 2 over 3 times t. Okay, and so that would be our new growth function for this new approximation of Moore's law, with t of being 3 years instead of the normal doubling every 2 years. Okay, and so that would be our function way to get. And again, it stems from t equals ln of 2 over k, and then we just had to solve for k, and so we divided by t instead. All right, so let's pause there and we'll come back for more.